look at some computer animations of what is going on here. So we are going to be learning how to find the volume of some like pretty strangely shaped figures. So what I have here in this program is I've just graphed two parabolas. The first one, I don't know why it goes gray every time I move my cursor there, but that first one is 4 minus x squared. The second one is x squared minus 4. Also, I would like for the adds to go away. There we go. And so currently I'm using upper and lower bounds of -2 and 2. And I'm using squares as my cross sections. So if I take right here, like for example, where that orange line is, the distance between the two functions. And if I take that and I build a square on it, so like the length of this side right here, however long that is, it looks like it's a little longer than 4. If I make a square that has that side length right there, then it would make a function right here. Maybe I need to click on that. Maybe that's what's doing weird. Okay, so if I do that all along, like right here, I'd have the tallest part, right? That's where my biggest square would be. And then as I go over here, I'd have smaller squares. And then over here, smaller squares. So basically, I'm taking like that base and I'm using it to build these like squares up. So if let's see where we got a quick click for this. If I click show slices, it is going to make this 3D figure. Currently, I'm just using 15 slices, but it would have like this shape here. As I use more slices, it becomes more of a solid figure there. So if I built this, I would have this like weird figure that looks like this. You've got almost that oval shape on the bottom, and then you got this weird like triangle look right here. For that, I can't remember what A does right there. Oh, that's just so, and you can see like all of those squares are across. Let me do a different function. So like let's just say we got y equals x plus 2, and I've got y equals, why is that not graphing it? Oh, because I don't put the y equals. I just need x plus 2. X plus 2. And then I've got x minus 2. And let's say that we only look, or sorry, negative x minus 2 is what I meant to have there. And let's say that we again just want to go from like -2 to 2. So I don't want to show the slices right now. So if I'm looking at this graph, I don't know, I need to kind of, how do I just reset this? It's got me confused. Oh wait, there we go. Let's turn this that way. So if you're looking like above, right here, there's our picture. And so you would have like a really big square right here. You would have smaller squares as you went in this direction. So if you put that all together, trace those slices. Wait, no, I'll show slices. It would, that's what it would look like with like very few squares. Shown as you make more squares, it would just become this kind of figure right here. It kind of looks like triangles put together for that. So I used to do this as a project. I haven't done it in a while because we haven't had as many things off, as much time after the exam. But I used to have them, they could do like different things. Most of them did not use square cross sections because the project gave you more squares so they get bigger. He cut these out. Said it was going to have a front and be a birdhouse, but I think he ran out of material, so he just did it like that and said it was an amphitheater for the birds to sit in and sing to the world there. So we definitely won't have enough time after the exam, and it's one problem, and it's kind of tedious, but we also used to have like 3-4 weeks after the exam, so we would spend some time doing that. So it gives you kind of like an idea of what you're looking at. So you can make all these like really cool different 3D figures that go, some of them might like make an actual figure that is like we know a formula for finding the volume. You know, if you think of taking, for example, let's see if I can do it. If I had let's see, I need square root, I don't know if it'll do this, of 4 minus x squared. Okay, yeah, it did. And then I had negative square root of 4 minus x squared here. Okay, so I've got it. If my base is a, oh no, I'm thinking of the wrong thing. I'd have to use a different shape. I have to use I'm thinking of a triangle. No, that's not right either. It would be, oh, here, yeah. Like if I used a base, for some reason this just says a circle and not a semicircle. But if I use a base of a circle and then I use like semicircle cross sections, it just gives me like a sphere, right? So sometimes they can end up being like actual things that we know the formulas for, but most of the time, like if I have this circle here, if I use squares, I get this kind of weird shape here. I could use triangles. It would give me a similar shape that's pointy right there. So what we'll be doing in this class, in this section, is we're learning how to find the volume of these things. So let's do a problem. Okay. Actually, first we got formulas. All right. So if we are going to find the volumes of solids with known cross sections, we are going to integrate the area function for the cross section that we know. So like today we're looking at squares and rectangles. So we will be integrating the formula for the area of a square or the area of a rectangle. These can be done perpendicular to the x-axis or perpendicular to the y-axis. Notice right here that if your function is perpendicular to the x-axis, or your cross-sections are perpendicular to the x-axis, you will be doing this problem in terms of x. If your cross-sections are perpendicular to the y-axis, you will be doing the problem in terms of y in this case. So you really just kind of have to see these problems done to know what's going on here. So let R be the region in the first quadrant bounded by y equals 1 minus x squared and the coordinate axes. Find the volume of the solid formed by constructing square cross-sections that are perpendicular to the x-axis on the base R. I actually think I might go over here and let you see kind of what we're doing for this. So in this case, it's first quadrant. So I think I'll just put in 1 minus x squared. And I want first quadrant, so I'm going to do, my lower function is just going to be y equals 0, which is just going to be the axis. And I only want to go from 0 to the intersection point right there, which is going to be 1 in this case. So it's not this whole area that we're looking at right here, because it's supposed to only be the first quadrant, but I fixed that by making my lower bound 0 right here. It won't let me go past right there on this. So if I wonder if it lets you zoom in. Oh yeah, it lets you zoom in. So what we're looking at, let's go with smaller slices, you can see it a little better, is, I've zoomed really funny though. I want it to. Okay, so let's use more than one slice. Let's not show the slices. Also, I need to go, all right, and we want a square right here. So, like right here on this line, I would take the length right there and I'd build a square, right? And then I'd move over a little bit and I'd measure how far it is across here. And I'd build me a square. Like if you were doing this project, that's what you do. You just kind of like measure across, cut out your base, you measure across, and you build yourself a little square, right? So I would be finding this square, and then this square, and then this square, and I'd find all of the areas of all these little squares. And then whenever you do that, you would end up with a shape that would look something like this, right? So that's what we're trying to find the volume of. Now, this lets you go with like very few slices all the way up to lots and lots of slices. What does that kind of make you think of whenever we have like very few slices? It's a limit as our number of slices approach infinity. A little bit like our Riemann sums, right? Because we had like all those rectangles that we would take and we would find the area underneath the curve, but then we would look at having more and more and more rectangles there. It's a similar idea of what's happening here. Thankfully, though, I'm not going to make you find like the area of all these squares and add them together like a Riemann sum and then learn how to integrate. On this one, we get to skip straight to the shortcut on this. So, we need to think about the graph here of the cross-section. This one would be without a calculator. But you just have 1 minus x squared. So if we think about graphing, black right there, on the x and y axis here, x-axis, we got y-axis here. This is just a upside down quadratic moved up 1 right here. And so it's just going to look like this right here, and we only care about the first quadrant. So what I'm highlighting right here would be the base of our function. Excuse me. And so the idea of what you're going to be doing is you are going to be finding, like you're going to be measuring across here, right? And then you're going to be building up a square that has that same length as whatever that green line right there is. So, you know, it's really hard to draw that in where you can really picture it well, but you know, you kind of picture that sticking up off of your paper right there. You're building that square. And then you move over and you do the next square and the next square and the next square. So what I need to know is I need to know the length of a side of that square, and then I need to make an area formula for that square, right? So, or area formula for a square is just side times side, right? So this right here is a side. How could I find the length of that side? Uh-huh. Okay, so that place on the function, is that your x-coordinate or your y-coordinate? You will get the y-coordinate, right? So like, this is vertical, so we're thinking of what the y is. Y equals 1 minus x squared. So we could take the top function and we could subtract the bottom function. In this particular case, what is the bottom function? There's really kind of not one, but it's the x-axis, which is just y equals 0 right there. So it's not really necessary to put that here, but there will be somewhere it is. So I'm going to point that out. So we've got top function minus bottom function gives me the length of that side. So the area with respect to x would be 1 minus x squared because it is s. I might should put that in here. Let me write it that way. All right. That area is going to be the side squared, and if we plug that in, we got 1 minus x squared. Okay, so that gives me that length of that side, and we are squaring it. This is what we're going to integrate, because that would, like, if I wanted to know the area of one square, then I'd have to pick a point, maybe it's at 0.4, and I plug in 0.4, and it gives me the area of that one tiny square, right? But then I'd have to do another one at 0.41 or 0.42, and even that's not going to be perfect because I am not doing every value. But in order to get the exact value, what we can do is we can integrate. It accumulates all those together. It like adds all of those squares together whenever we do this. In this case, we're in terms of x, so we want to look at our x-axis for our limit. So we would go from 0 to 1. And then we're integrating our area formula, which is 1 minus x squared dx. On some of these, it will just be set up something like this. They probably would actually have you solve out. How do I solve that? Like, to finish out, like, get a number for my answer. That is exactly what we've got to do, because if we try to do like a UDU substitution here, the derivative of negative x squared is negative 2x, and you can't do a UDU. So you're going to expand it doing square, double square. So you'll get 1 minus 2x squared plus x to the 4th dx. So all I'm doing there is doing 1 minus x squared times 1 minus x squared. That gives me what I'm looking for here. Okay, questions so far? All right, then we're going to integrate. So whenever we integrate, we got x minus, we'll get x to the 3rd here, so we'll get 2/3 x to the 3rd. And here we're going to increase our exponent by 1. We'll get a 5. We'll get 1/5 here. This needs to be evaluated from 0 to 1. And so I will plug in 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the 5th minus, then I'm going to plug in 0 minus 2/3 times 0 cubed plus 1/5 times 0 to the 5th. All of the stuff in that second parentheses is just going to be 0. In the first parentheses, I'm going to get 1 minus 2/3 plus 1/5. And so if we get common denominators there, we'll get 15 over 15 minus 10 over 15 plus 3 over 15. And we will get 8 over 15 will be our volume there. Okay, questions? All right, let's try another one. Okay, so for 2, a solid is formed with rectangular cross sections perpendicular to the y-axis. So when you see this perpendicular to the y-axis, you might want to like circle it or something. Here, if you see perpendicular to the y-axis, that means your problem needs to be a dy problem. Everything needs to be in terms of y. So a lot like we were doing with our area between the curves, it needs to be right minus left. All of our limits are coming from the y-axis. It's going to be, we're going to look at it differently than we looked at the x. The height of each rectangle is 3 units. The base of the solid is the region bounded by y equals 1 over x, y equals 1, y equals 4, and x equals 0. Find the volume of the solid. So we need to sketch a graph first of what this is going to look like. I've got y equals 1, y equals 4, x equals 0. I would do those first to kind of get a bearing of where you need to be. In this case, it is going to be pretty much all in the first quadrant. So y equals 1, horizontal line at 1. Y equals 4 is a horizontal line at 4. X equals 0 is the y-axis right here. And then the one that matters the most for you, this y equals 1 over x. If you're unsure, you can just like make a table for it. So if we've got y equals 1 over x, if we plug in, if we plug in 0, we won't get anything, right? Because that'll be undefined. But if we plug in 1, we'll get 1 divided by 1, which is 1. So we got the point 1, 1. If we plug in 2, we get 1/2. And this is feeling not the most helpful here. Actually, let me change my limits here. So what's happening is really I need to see I'm going to put 1 right here and 2 right here. I'm going to spread it out a little bit more so I can see it better. So if I plug in 1, I get 1. If I plug in 2, I get 1/2. So this graph it's going down like this, right? When would I get 4? Because it needs to go up to that point right there. 1/4, right? Because 1 divided by 1/4, dividing fractions is easy as pie. We can flip the second and multiply. So if I had 1/4 right here, so this graph starts to look like this. And it is a good thing that they told us that our cross sections are perpendicular to the y-axis, because if they're perpendicular to the x-axis, then I've got to do it a lot differently. I've got to do a different problem. So it tells us that our cross sections are perpendicular to the y-axis, which means I'm going to be taking like a strip somewhere, doesn't matter where we pick, to kind of draw this in right here. And this is going to be like the length of my side of my rectangle, one side of my rectangle. I don't really want to call it x or y because we're using those variables. You could call it length or width if you want. I like just sticking with s here. It doesn't matter what you do. And then you're going to be building up a rectangle that is, the height of it is 3 units tall. So if I make me a rectangle right here, I realize the 3 here is not to scale at all. That has a height of 3, right? What is the area of that, what is the area of that rectangle? It's 3 times S, right? Okay, I need to come up with a way of talking about S that doesn't have S in it. It needs to have, in this particular case, Y, because I'm perpendicular to the Y axis. So S is going to equal right minus left. Okay, if it were X, in terms of X, it'd be top minus bottom, but in this case, it's going to be right minus left. Now, I do have to be careful here because Y equals 1 over X. This is in terms of X. I need to solve this so it's an X equals equation. Because if we are doing things in terms of Y, we need to have Y's in the formula. So I would have to multiply by X. So XY would equal 1. And I divide by the Y. So this formula is kind of a interesting formula because it is almost the same whenever you solve it for the X or for the Y. So this formula right here is 1 over Y. Our left-hand side here is on the x-axis. That would have a y coordinate of 0, right? It's y equals, x equals 0. So in this case, we would be doing, the length of that side would be 1 over y, and we would subtract the right side, the left side, which would be 0. Again, 0 is not totally necessary, but sometimes you'll have a different function there, so I like to put it. So S right here is really just 1 over y. Okay here. And that is coming from the fact, no matter where I put that like horizontal strip right there, the right end point is on the purple graph, so we use it first. And then the left end point is on the blue graph, so we subtract it. So what I want to do to get my area formula, which is the formula I'm going to integrate, is I need to take this S and plug it into the area formula for a rectangle, which is, in this case, because they tell us that the height of the rectangle is 3, it's 3 times 0. They could have told us it was a different height, like 4 or 7. Or we'll see one where it's, the height is like twice the width or something like that, which makes it a little harder. So in this case, we're putting 1 over y right here. So our area formula would be 3 times 1 over y, which is probably going to be better if we just write that as 3 over y. So that formula gives me the area of a rectangle. That is what I need to integrate in order to find this volume. So what do my limits of this integral need to be? Okay, 1 and 4. Not 0 and 1. There, because this is a dy here, we have to look at the y-axis. And the lowest point is 1, the highest point is 4. Okay, look back through that, because the setup of these can be a little bit tricky at first. And the setup is most important because the actually solving them is usually, so a lot of these questions, like the one we did in the warm-up, don't even ask you to solve the problem. They'll just ask you to set it up. And questions? Okay, so we're going to integrate this. When I integrate 3 over y, what am I going to get? 3 natural log absolute value of y, because that's just the same as 3 times 1 over y. And when we integrate 1 over y, we get natural log. We are evaluating this from 1 to 4, and so we'll get 3 natural log absolute value of 4 minus 3 natural log absolute value of 1. Absolute value bars are not entirely required there because 4 and 1 are both positive numbers, so if you left them off, that would be fine. What is natural log of 1? It is 0, so that's going to go away. I'm just going to get 3 natural log of 4. But sometimes they don't leave that as the answer. For that, definitely, I mean, if it's free response, you can leave it here with that natural log of 1. That's fine. If it's a free response, you can just stop right here. But there's a decent chance they're not going to leave it as 3 natural log of 4. Anybody have any ideas of how we could make that difference?
Can you put 3 somewhere else?
Okay, that is an option. It could be natural log of 4 to the 3rd power. So in that case, that would be natural log of 64. That is an option. What I think they'll probably do is go the other direction with it, though. So, like, that is it. Like, this could be an answer. This could be an answer. Technically, the one in between could as well, but I highly doubt they do that. What I think they'll do, though, is I think they'll go the opposite direction with this. Natural log of 4 could be written as natural log of 2 squared, right? Then what could you do with that exponent right there on that 2? You could take it out front, so that would give you, 3 times 2 natural log of 2, which would give you 6 natural log of 2. This I have seen them do on some multiple choice questions before.
Why would they do that? Like, what is the point?
It's more simplified because your number you're taking natural log of is smaller. There, but it's a little tricky because what I would see on things like that is that a lot of people could get the right answer, but were missing it because they didn't know what they were doing with those natural logs. So I have seen some like released multiple choice questions that did that before, so watch out for it. Anytime you see a natural log of 4, there's a chance they did that with it, or a natural log of 8, or anything that could be written as like a power to another power. What you'll usually see with this too is like all of your answer choice, none of your answer choices will have a natural log of 4. So maybe try to think about, oh look, they're all natural logs of 2s. Where'd that 2 come from? It doesn't make sense. That could be what they did for that. Now, free response, I wouldn't even bother replacing the natural log of 1. I'd leave it here for that. Okay, let's look at another one. Okay, find the volume of a solid with a semicircular base of radius 5, whose cross sections perpendicular to the base are parallel to the diameter and are squares. This one is extra difficult because they gave you one number and no equations at all. And this does not make a solid that we like know the shape of, right? So it's not going to be one that, like some of these, like it's just going to be a cylinder. So you could just use the area of a cylinder, right? Although that's not going to happen to you very much. This one is, if it was a semicircular base with semicircles as its cross section, it would be just like half of a sphere for that. But if it's got square rectangles or square cross sections, it's different. So in this case, I need to take a semicircle and I need to put it on the XY plane, right? So you guys have not learned like an equation of a semicircle, but you have learned the equation of a circle. The easiest thing to do with a circle is to put it with a center at 0, 0. And if I have a circle with a center at 0, 0, its formula is x squared plus y squared equals the radius squared. And in this particular case, what's the radius? 5, right? It tells us right here the base of the radius is 5. So x squared plus y squared is going to equal 5 squared. So x squared plus y squared equals 25. So that would be the equation of a whole circle. Here. We only want half of the circle. What we can do for this is we can solve this equation for x or for y. It does not matter whether you solve it for x or for y. In this case, I think it's easier to stick with solving this stuff for y because we're just more used to seeing equations in terms of y. So if I want to solve this for y right here, Tyler, how would I do that if I want to get that y by itself? If I'm solving for y. Yeah. So I'll subtract that x squared. So I got y squared equals 25 minus x squared. And then what would I need to do, Tyler? Good. And when I square root both sides, what do I need? Plus or minus the square root of 25 minus x squared. And when you do this, that's really two separate equations. It is really y equals positive square root of 25 minus x squared, which is going to give you positive y values. So it is the top half of the circle here. And then it's y equals negative square root of 25 minus x squared, which is the bottom half of the circle. In this case, does it matter whether we use top half or bottom half? It does not. I would definitely choose top half because there's no sense in doing a problem that has an extra negative that you don't need to deal with. So I would choose the top half of this circle right here, which is this equation.
Can you go ahead and change that to 5 minus x? Would that be right?
No, can't do it because things that are like added or subtracted, you cannot take the square root of them separately. Because, for example, if you had something like the square root of 25 minus 16, that is the square root of, oh, I haven't picked one that actually works, have I here? 25 minus 16 would be square root of 9, which is 3. But if I square root them separately, I'll have 5 minus 4, which would just give me 1, which would not be correct. So if they are added or subtracted, you cannot take the square root of them separately for that. So in this case, I'm going to use this one that I have highlighted here. The bottom half I'm just not going to worry about because they told me that this was that I only need a semicircle base. And then cross sections perpendicular to the base are parallel to the diameter and are squares. So if they are, oh gosh, did I even really want to do this way? Because here we are parallel. I wish they'd said perpendicular, but they didn't. Parallel to the diameter. So if my cross sections are parallel to the diameter, they actually go this way, right? Which means by solving for y, I'm actually going to have to do this in terms of x. All right. By solving for terms of x, I'm going to have to do it in terms of y. Gosh. change problem. It's okay. It's okay. It's fine. Y's are not particularly more difficult necessarily for this. But it does mean if I'm doing this parallel to my diameter, that my cross section here is going this direction. Here, so this would be my S right here. That's the length of my side, and I am making squares that stick up off the page right here. What is the area of that square if we're just using S's? S times S, which I can just write as S squared. Because S is horizontal for me here, I need to do right minus left for my S, but it's the same function, right? So I can't subtract itself, that'd just give me 0. So where this S crosses the y-axis, it's perpendicular to the y-axis. I actually have to do this in terms of y. So I've got myself all mixed up by doing it this way. But it's really not that bad because this equation right here, x squared plus y squared equals 5 squared, if I solve it for y instead, for x instead, I would subtract the y squared. So x squared would equal 25 minus y squared. I would square root both sides, and I would get x equals positive square root of 25 minus y squared, and I would get x equals negative square root of 25 minus y squared. Okay, the positive part in this case would be over here. This would be x equals positive square root of 25 minus y squared, and then the negative part would be over here, and that would be x equals negative square root of 25 minus y squared. So my S is going to be the positive part, square root of 25 minus y squared, minus the left part, which is negative square root of 25 minus y squared. What happens when I got that double minus right there? Turns to positive. So S is going to be a little bit easier. If I add those together, that's going to be 2 square root 25 minus y squared. We could have very easily done this in terms of x's. You still have to switch. It still has to be, it'd be the same formula, but it would include x's instead of y's if you did it the other way. Here, so that is my S, but I don't want to integrate S. I want to integrate the area formula. So if I take S and I plug it into the area of a square formula, I will get my area formula is going to be 2 square root of 25 minus y squared squared. And so when I square that, those two things are multiplied, so I can square the 2 and the square root separately. So 2 squared would give me 4, and then when I square the square root, they cancel, so I'd get 4 times 25 minus y squared, which would probably be easier if I distribute there and get 100 minus 4y squared. We're just about to get there. We need to integrate this area formula, 100 minus 4y squared, with respect to y. What should I use for my limits? Hello? I do. Yes. edgiest. Someone needs to go see Coach Foster. But she stepped out. I will. She'll probably be back in a second. It's okay. Hopefully. Unless he sees her in the hall and thinks she's on the run.
Yeah.
There. It didn't sound serious. So, alright. Yeah. Not negative 5 and 5. Because those values come from the x-axis. And we are doing this in terms of y. So, y-axis, it's going to be 0 to 5. Because we're only doing a semicircle base, right? We're not doing the whole circle. We're only doing the semicircle base. So, we'll go 0 to 5. Here. I mean, when he's more angry, you can definitely tell. Yeah. Okay. So, we've got, here we're going to integrate, we'll get 100y, and then we'll increase the exponent by 1, and divide out front by that exponent, and then we will evaluate this from 0 to 5 here. And for the sake of time, we're going to pretend that this is a free response question where all we've got to do is plug this in. Here, and we could just leave it. I mean, it's still not that bad to calculate, but we'll just leave it for the sake of time here. Okay, questions? Okay, this one is calculator active, so we are going to graph it. And so if we graph it, we got y equals x plus 3 and y equals x plus 1 squared minus 5 here. And I am going to screenshot that here. Okay, so for this, we've got a solid is formed with rectangular cross sections perpendicular to the x-axis. So my cross section here is going to be perpendicular to the x-axis. That means it's going to be vertical there. That's going to be my S. And then our area formula is for a rectangle. So the rectangle that we're drawing in, Coach Foster needed to see you for a second. Here. So our rectangle here is going to have a base of S. What's the height of that rectangle? If it was S, it'd be a square, and they would have called it that. It is 2S. Okay, so notice like the difference in the other rectangle problem that we did. In the other rectangle problem, we just had a height of 3 for all of the rectangles, right? So it was just 3 times S. In this one, it said the height of each rectangular cross-section is twice its base being S right there. So the area here could be 2S squared for this one. So we need to tell what S is in this case. S, we are going to do top function. What's our top function? So we're look at that like strip right there. You're looking at the top endpoint. Which one are we on? X plus 3 minus the bottom endpoint of that little strip that we call S. What is it? X plus 1 squared minus 5 right there, which I guess does need even like that extra bracket because the negative goes with all of it. And so our area, we can take all of this, you can see why they're making this calculator active, and we can plug it in for our S. So we'll have 2 times X plus 3 minus X plus 1 squared minus 5 squared. Right, that would be my area formula, which is what I need to integrate. What are our limits for our integral? Oh, can we even tell for sure? I can't tell on this if they're, I can't tell for sure if they're exactly at, oh, they're not. This intersection point right here, we're looking at the x coordinate because it's in terms of x. We got negative 3.19258. And then over here, for the other intersection, we've got 2.19258. There. So this is what we're going to integrate. I should put a dx over here on the end. So you actually could do this. You could call this f and this g. It might make it easier right here because then you could do integral from, what was it again, negative 3.19258 up to 2.19258 of, and you can do, you got to do 2 times, the red graph is, I've called f of x minus g of x squared dx. So get your answer, which is going to be 301.928. Everybody okay there? Our textbook actually does not have a lot of these problems.